Hey guys, welcome back to another video. So in this video we'll be talking again about bioreactor control units. So it's just a continuation video of the previous video. So if you haven't watched my previous video, so do give it a watch for your entire reference. So we'll just continue from where we left in the previous video. So moving on with that. So we talked about exit gas analyzers in the previous video. We talked about some of the terms and conditions and some of the mechanisms related to exit gas analyzers such as paramagnetic analyzers and flame ionization detectors, mass spectrometer, and all of its uses. As you can see, I have covered all of these in my previous videos. So moving on. So there are some of the pictures related to the exit gas analyzers. As you can see, this is the thermal conductivity analyzer, this is the long path infrared analyzer, this is the mass spectrometer, this is the flame ionization detector. So these have all of the labeled stuff, as you can see on each of the diagrams. So you can just give it a read. So moving on with this. So we'll talk about some of the measurements from liquid slip stream. So we'll talk about some of the stuff with the liquid strip stream. So which includes the HPLC. So HPLC is something that is very related with the term known as chromatography, because its full form says that it's a high performance liquid chromatography. So it's a measurement from liquid slip stream. So and there are other mechanisms as well, such as HPLC, we have mass spectrometers, we have enzymatic methods as well. So talking about HPLC, so it is dissolved organics and particularly useful for proteins, and it's an autoanalyzer as well. Also it's highly specific and compounds need not be volatile, response time is long, and solids must be removed by filtration. Membrane fouling can be a problem, and guard column must remove compounds that may foul columns. Expensive as well. Main value is to differentiate among closely related proteins or variants of a particular protein. So basically it separates the stuff or the different strains of proteins as well. So HPLC does the work. Also talking about mass spectrometer, so we just saw the picture of a mass spectrometer previously. So the mass spectrometer is used for dissolving compounds that can be volatilized, and it's the same instrument that can be used for exit gas analysis as well. It's a rapid, it's specific, and as well as it's expensive as well, and it's a complex molecule present problems. So with the use of complex molecule, it may not be that much handy. All right. Also talking about enzymatic methods, so it has a potentially wide range of action, but glucose has received most attention. So mainly we use it for glucose, and it has a slow response, that's a drawback, and not highly flexible but very discriminating, and potential for contamination, and has limited acceptance. So this is not a very much useful method, but definitely you can count it as one of the methods, as you know. So this was the measurement from liquid slip stream. So we talked about some of its measurements with the help of HPLC, mass spectrometer, and enzymatic methods for a bioreactor. So moving on with, so we'll just talk about the instruments for measuring parameters. So we'll talk about some of the important and the essential instruments for measuring some of the important parameters that may control the chemical environment, definitely. So first one is the online mass spectrometer. So we are coming across the term of mass spectrometer again and again, so you can understand how important it is. So it is definitely used for the measurement of volatile components. So it's a measurement, so it's a definite and a proper use for measurement of volatile components. So next we have the HPLC. So we just now studied about HPLC. So HPLC can be used for separating different strains of proteins and different set of molecules. Also we have the online NMR. So NMR definitely does the job. At different wavelengths it works to separate stuffs and also to measure it. We have the Fourier transform infrared spectra analysis. So FTIR is another instrument for measuring a different sort of substances and molecules. So there are some of the problems that people have encountered with the use of these instruments. So some of these are fouling, pardon. So there may be we may obtain results such as false positive or false negative. So these may cause this may be caused due to probe fouling. Also, extended period of fermentation can disable the probes. Definitely, is just not an indefinite process. It has its own time. It has its own limitations. So extended period or period over the maximum may affect the sensitivity of the probes. Also, drift of set parameter in a probe. So the parameters set in the probe may drift apart or may get changed due to some or other reasons, and there are definite chances of contamination in every other processes. So we'll talk about fermentations and all the processes related with biofermenters, bioreactors. So the chances of contamination is the first and the foremost point, or the main point that needs to be taken care of. So because if the particular bioreactor or any of the fermentation tank gets infected with any number or very small amount of contamination, the entire process gets futile. All right, so it all loses its importance if the bioreactor gets contaminated. So we have to reduce the chances of contamination. So moving on with, so we talk about some of the data loggings. So what all we have to note while conducting a bioreactor or a fermentation system. So what all information we need to collect and what all information we get. All right, so importance in the food and pharmaceutical industries. So it plays an important role in the food and the pharmaceutical industries. It monitors manufacturing batches, so it measures the time and amount and all of the technical stuff. It assures the quality of the product that we get after fermentation. Also consistency from batch to batch. So these are all our stuff that we get from data logging. So data logging is the stuff that are used by bigger farms, bigger industries, for calculating every other minor changes and major changes for all of the stuff, such as measuring so ensuring quality, the measuring the time gap and all of the stuff. And also these are used for the future use as well. Also controlling examples. So some of the controlling examples here we have is the high cell densities, so which is more than 15 or 20 gram per liter for E. coli was impossible. So metabolic analysis, how the buildup of acetate is considered. An acetate is a toxic metabolic byproduct. So it shows that use a controlling example is the not using of or minimum usage of acetate, cause acetate is a toxic metabolic byproduct and hinders cell growth, and control strategy is to feed glucose at a rate. So basically, like all of the data logging stuff, we get to know how the process works, how quickly we can achieve greater products or better products at a minimal time, at a minimal cost. So from all of the data logging stuff, from all of the technicalities and all of the time and all of the calculations, we get to know which one we have to put and fit the right equation at the right places. Such as in this is just an example which shows that while considering for high densities, if acetate was used, so acetate is definitely a toxic compound or a toxic metabolic byproduct. So for that, it can be replaced with glucose. So glucose has no side effects and it is not at all toxic, and it maintains moderate growth rate, and whereas acetate cannot. So these are some of the stuff that we get to know from data logging. So moving on, so this is a software for antibiotic fermentation clone. So this is an entire huge stuff. So this is not important for you all. So this is just for the information, so you can just give it a look. So these have analog input system, analysis values, digital input devices. It has open loop control. These have all of the stuff like these, balancing short-term trend, long-term alarm signals, and calculation of mean values, balancing plant flow diagram and everything, and monitor color graphs. So all of these stuffs we have, which controls and controls the entire fermentation process. So moving on with this, so let's talk about sterilization. So one of the important topic of fermentation is sterilization as well. So there are main two, so I'll just like to discuss before moving on this. So there are basically two main types of this. First is to removal of contamination, that is done by sterilizing. So sterilization is the first and the foremost important thing to be taken care of in order to minimize the contamination rate. So sterilization is achieved through thermal death. So thermal death is basically death of certain sort of microbes that are unwanted through providing temperature at a higher rate than the normal, alright, for a limited period of time. So basically thermal death leads to sterilization by death of microbes. It is basically by inactivating living cells, as said, spores or viruses. And probability of extension of the total population P0T is given by POT, which is the extension of total population as POT, equals to, in bracket, 1 minus PT. So PT is the probability that an individual will still be viable at time T to the power of n0. So n0 is the number of individuals initially present. So this is the probability. So this is the entire term is the probability of extension of total population, which is given by POT. So also probability of death. So this term, this PT is given by, so over a period of time it is given by following expression, which says e to the power of minus kd by t. So kd is the death rate or the death constant, and pt is and t is the time, and pt is the probability of death over time here. So this pt can be written as this. All right, so this is the entire probability of extension of total population, in which this pt can be given as pt equals to e to the power of minus kt by t, kt into t. So we have a survival curve as well for here. So this is the typical death rate for E. coli in buffer, where n is the number of viable cells at any time and n0 is the original number of viable cells. And typical death rate for spores of Bacillus stereothermophilus in distilled water, where n is the number of viable pores at any time and n0 is the original number of viable pores. So as you can see, thermal deaths are definitely caused at high temperature. So you can see 121 degrees. So 121 degrees is achieved mainly when autoclave is done. So autoclave is a sterilization process that is carried out for sterilization or ensuring that everything is sealed or contamination free. So at higher temperature, the death rate is caused immediately, or the thermal death is caused immediately. So the graph, you can see a steep decline from here to this, and also with time, so with the loading temperatures such as 105 degrees, so it takes a little bit of time, but it definitely causes death. So as you can see, as you increase the temperature, the graph gets steeper, as you see it. And it's same here. So we have n by n0. So n is given by number of viable cells at any time, and n0 is the original number of viable cells. So with this, so let's just talk about some of the important terms or the inactivation agents for sterilization, for ensuring sterilization. So talking about the first thing, which is the thermal inactivation. So thermal inactivation is ensured by sterilization by heat, economic process for large scale fermentation systems, and heat sensitive equipment must be sterilized by other processes. All right, so these are some of the easy steps. The second step is UV inactivation. So UV cannot penetrate fluids. So UV cannot penetrate high amount of suspended material. So to an extent UV can be used, but definitely definitely can be used, but not a pretty much reliable source. But X-rays are definitely a very stronger source, because it can penetrate more deeply, and also it has a drawback that it is a costly method. So our cost efficient, so maintaining the cost is the most important and a tough job while considering all of these reactions. Also, safety considerations are important concerns. So this. So talking about the last part, some of the last parts, which are the chemical inactivation agents. So some of the chemical agents for sterilization must leave no residues. So it can be toxic to the next culture. Also, ethylene oxide can be used for sterilization. So ethylene oxide definitely adds to a lot of these for ensuring sterilization. Also, 70% ethanol water mixed acidified to pH of 2 with HCl is a deadly combination for ensuring sterilization. So 70% ethanol, where ethanol containing 70% of ethanol with the water mix acidified to pH 2 with HCl. So 70% ethanol is basically maintained at a pH 2 when we add HCl. Also, it kills vegetative cells and spores. Formaldehyde solution is used for fixing, and sodium hypochlorite we have also for sterilization or disinfection, and effective for small scale and heat sensitive equipment. So here we have a lot of chemical agents, as you can see. All right, so here we have ethylene oxide, we have ethanol, we have formaldehyde, we have sodium hypochlorite. So we have a lot of them for ensuring. So we have another graph here. So it's the overall survival curve for a system with three distinct subpopulation. So population A is normally dominant. So population A is normally dominant, as you can see a steep curve, but it is the one of the most sensitive to sterilization agent, while subpopulation C is far more resistant. So C, you can see it's written that the subpopulation of C or C is far more resistant. So it takes time to die, or takes time to cause or get sterilized. All right, so you can see a not a very steep curve, it gradually dies, as A is not very much resistant and sensitive, very sensitive, so it dies naturally and very quickly. So this is a simple graph. So there's another thing which is the some of the terms related to sterilization. So for some of the sterilization terms are steam sterilization. Let's just talk about steam sterilization first. So steam sterilization is a very easy process which is carried out by autoclave. So if you, so I guess some of you guys know, and those who do not know, so autoclave is a simple process. It's basically a cylinder like this. In this we keep our racks or particular inoculum or particular vessel in which we have the particular microbes or bacteria to which we need to sterilize, for which we need sterilization. So basically we have a lid here as well, so we close the lid and we switch on the button. So basically what happens is that this machine, let's say this is an autoclave machine, so this machine reaches a temperature of 121 degrees Celsius in about 15 to 20 minutes, and it sterilizes the entire cells or the entire compound whatever we have kept in. So after some time, after the sterilization has been done, we can take out this the stuff we have put in and do our work accordingly. So batch unit allows long time, moderately high temperature sterilization, and definitely does the job. And this is a sort of a autoclave thing. So it's a long process definitely, cause 121 degrees is just not a easy step, cause reaching 121 degrees Celsius sometimes takes very long. So it depends on machine to machine. Older machines take a very long time, and after reaching 121 degrees Celsius it takes about 10 minutes at 121 degrees Celsius to ensure sterilization. So it's a long time, moderately high temperature sterilization. With this we have a continuous sterilization here. So continuous sterilization is a short time, definitely. Continuous sterilization is like we provide a large amount of temperature at the word go. So definitely like as soon as we start the reaction, the temperature is increased to that much, or the temperature is set to that much, and we start, and as the temperature we have increased already, the temperature is to a high temperature, it's already set to a high temperature. So whenever we put the cells into that, so it gets immediately sterilized and does not take much of the time. So it's a short time thing and high temperature sterilization. So definitely this thing, as you can see a graph, so whenever we put the cells, these cells are already the cells where we put the thing is already at a very really high temperature, and we put it at that thing and it gets sterilized immediately. So it's a tedious process. So coming to the last thing, which is the filter sterilization of air. So filter sterilization is an easy thing, very easy. So as you can see from the wordings here, so depth filtration technique primarily involves physical effects such as inertia, blocking, gravity, electrostatic attraction, diffusion. So depth filtering technique is some of the techniques that that you can see here. So it's a glass wool or a glass fiber that is present here. So it's an entire thing, it's just like a net through which we provide air inside it, and this is an outlet for air. So as soon as we pour the entire medium or everything that we have, it gets filtered or gets sterilized, or all of the things get manipulated just like this. So glass wool filters can be subjected to steam sterilization and reused. So glass wool filters are used whenever we keep the substance in a autoclave or in a jacket or in a box like thing which works under this. So these are some of the filters that we generally use to cap it on the top of the vessel and keep it in autoclave so that no air or any other contaminating substance get inside it. So definitely it adds to the sterilization process. So this is one of the more process that involves in sterilization. So that's it from my video. So hope you enjoyed the video. So if you enjoyed the video, please give it a like and do subscribe to my channel, and I'll see you in the next one.